So today's topic is application delivery networking. In the data centers, application delivery is the key reason for having a data center, but we will define exactly what that means and how is it done. So there are application delivery controllers, what they are, and most of them are based upon load balancing. So what is load balancing? Network address translation, that is also used by load balancing and other ADCs, and then we go through lots of other ADCs. So application and delivery in the data center, actually there is lot of what we call replication and partitioning. Okay, and depending upon the definition, some people would call it all load balancing, but we are going to distinguish here between the load balancing and partitioning. Basically, load balancing is done when you have a replication, when you have many copies of the same thing. So you have a server, you are running a web server, you might have 4 or 5 computers doing the same web serving, because you have just a big website, a lot of users. That is the replication. And so when you have lots of servers doing the same thing, then you need to put a load balancer in front of it, and then the load balancer decides which server to send your request to. Right? But then there is something which we call partitioning. Partitioning is when you want to divide the application into pieces such that, for example, you take a YouTube application. Now YouTube not only serves the video, but also has a directory of all the videos, has your account information, has many other things. So it could have a different server for each of those pieces. In that case, there will be some box here in front of the servers. It will look at what is the request about. If it is about the video, it goes to server 1. If it is accounting, it goes to server 2, and so on. That is content-based partitioning. Context-based partitioning is that depending upon when and how and who did it, the request will go to a different server. For example, if it could be application context, for example, if it is a read, it goes to server 1. If it is a write, it goes to server 2. All right? Maybe read server 1 is very fast, and write server 2 is good for writing, whatever reason, okay? And then user context. If it is a window user, send it to this server. If it is a Unix user, send it to that one. If it is a laptop user, send it to that server. So depending upon what the user is, what operating system they are using, what browser they are using, what is their context, you send them to a different server. For example, in particular, you will send a mobile user to a different server. I mean, you don't want to send an iPhone user to the same server that puts out this big page for laptop guys. All right? Multi-segment. So now all of this, so you see now, understand the difference between replication and partitioning. Replication is when people are doing the same thing and you just want to do load balancing, simple load balancing. And partitioning is when you want to really know the context as to what is happening, either on the content itself or on the user end or the application end, and so on and so forth. In each of these cases, there are multiple TCP segments. So for example, if there is a ISP proxy, which is in the case of Google, there is a Google proxy, there is a TCP connection from the user to the proxy. From the proxy to the load balancer, there is another TCP connection. From load balancer to the firewall, if there is a firewall, from the firewall to the server, and so on and so forth. So even though it looks a single TCP connection to you, it is not end-to-end. Okay, it is broken at many places, which is totally transparent to you as a user. You send a request to connect to www.google.com. It is caught by proxy server at WashU first. And it says, I already know the answer to this question, so I'm going to send you the answer right away. And it doesn't even waste its bandwidth to AT&T to respond, to find that answer. Right? So that is like ISP proxy or enterprise proxy, and so on and so forth. Any question about this? All right. So then there are application delivery controllers. Actually, in this slide, I had already shown you lots of boxes. We call them middle boxes. Why they are called middle boxes? Because they are in the middle. Here is one end, there is the other end, and in the middle, right? So they are middle boxes, and another name or a better name for them is application delivery controller. It will become clear as to why we call them ADCs, but they are all middle boxes. The old name is middle box, because the original IP was not designed for this. It was designed just end-to-end connection, and later on people started putting middle boxes. Yeah.
So I have a question. When I send a packet through the TCP connection between the middle boxes control the TCP, or just servers?
Yeah, exactly. So the thing is, you are thinking that you are talking to here, but you might be talking to a box over here, and this will be talking to that box, and this will be talking to that box. So there are many segments in between.
So eventually the servers have the TCP control.
In some cases, it doesn't have to go eventually to the server. Yes, it could go to the server. It could come back from the proxy. All right. So we call it network service, a task that applies to multiple applications, such as security, monitoring, acceleration, offload. These things are not, they may not be application specific. Web server can use it, file server can use it. For example, login. Okay, many servers can use it. And so intrusion detection and so on and so forth. So these are all what we call services, network services, which are really not specific to an application. Actually, they would be used for a particular application, but they can be used for multiple applications. And therefore, several applications can share a service. All right? And the appliance that provides the service is called an application delivery controller. And so and the people who started selling it, in particular, like every time we talk about something, we talk about a company. So the virtualization was started by VMware, and they are still the leader. ADCs was started by F5, and they're still the leader. So basically they call it ADC. And so you could have a load balancing ADC, you could have firewall ADC, you could have proxy ADC, you could have SSL offload ADC. By the way, what is SSL? Yeah, secure socket layer. This is the one that you use HTTPS. I think we talked about that before. So the thing is, many applications use SSL. Not only HTTP, you have HTTPS, but there is FTPS, there is other applications that can use, and it's the same SSL. So you could have a box which can do that for all the applications. All right, you already know firewall, proxy, and load balancer. Now, load balancer is an example of our ADC, but also the basic components of most ADCs. So this is going to be discussed in a lot more detail. Other ADCs are firewalls, reverse proxies, TCP multiplexers, and HTTP compressors. And we will discuss those slightly later. So the load balancing. The advantage, and this is why F5 came into business, is because the data centers were expanding and they could not do all the work on one server, so they were putting lots of servers. Once you put lots of servers, you need something in the front that can direct the request to different server every time. Right? And the advantage of this is once you get this box, you can have 3 servers today, 5 servers tomorrow, 7 servers day after, and 3 servers day after that. You could change the number of servers. The customers don't know anything about that business. You don't have to have 3 addresses. 3 names, www1, www2, www3, and things like that. Just have one name. All right. So it allows adding servers as needed. Now, on the server side, 2 terms are used that you should be aware of. Basically, one is called server cluster and server farm. What is a farm and what is a cluster? And from the name, it appears that the cluster looks like something small and farm looks like something big, right? And so that's what it is. A cluster is a centrally managed set of servers working together on one applications, and they appear as one server. So even though this is one server, this might have not only 16 cores, but they could have 16 blades in it. All right. So that is the whole thing, one cluster. As far as we are concerned, is just like one server. A server farm is a big room full of servers. Okay, and they could be working on different things, or they could be working on one thing. It doesn't matter. But their farm is a big thing, and generally independent. Okay, server farm and server cluster. Then probes. So the load balancer, the way it knows that what is up, what is down, is that it sends a hello messages every so often to the servers, or ping messages to the server to figure out whether it is up or down. Those are called probes. Virtual IP, VIP, is the address to which the customers connect to. So the customer really don't connect to the server, they connect to the load balancer, and the IP on this side is what we call VIP, virtual IP. On this side there is a real IP, RIP. So VIP is the virtual IP, which is the customer facing IP address. Now you understand the term facing, customer facing IP address. So load balancer has two IP addresses. One is customer facing, one is server facing. Every port has an address, right? So stickiness table. Now when a server connects you to one server, your first your TCP connection goes to server A. Then you say, I want this data, you cannot send it to server B. That would be crazy, right? So once somebody has been connected to server A, all their TCP requests, they'll have to go to that same server A. So the load balancer has to keep that state in a table somewhere that, okay, IP address X was connected to server 1, and therefore whenever IP address X comes in, we send it to server 1. That is called a stickiness table. Not on that TCP connection. That would be that would really confuse, unless you do. So here's the thing: unless you do segmentation, in which case the TCP connections are not going there; they are just ending right here. Right? In that case, you can send one request here, second request here, third request there, because the customer doesn't know, right? But if it is if the TCP connection somehow, that is a mode 2, by the way. It doesn't have to end TCP connection here. It could just look at the message and send it. Right? So in that case, it has to stick. And predictor is actually just the rule or the policy. This is just the rule or the policy that is used to balance, basically to forward. It could be simply round robin, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Least connections, or we keep track of how many connections are there. Hashing, which is random, or least loaded. This is difficult. I mean, least loaded would be ideal because we are load balancer, but then you have to manage every microsecond and millisecond what is the load on every server. And it's not worth the hassle. Okay? Now, I'm using these terms because these are the terms that are actually, I mean, there might be other names for it, but these are the terms that are used at least in one company's product. Okay? And again, the leader. Can you guess? It's not F5 in this case. It's actually Cisco's product. Okay, I mean basically Cisco is a networking guy, and they just and in their products they use this thing. Anyway, so the names, in particular these names, predictor and the sticky table. VIP is general enough. Probes is a very general name, but at least. Anyway, so layer 4 switching. So now what does the load balancer look at? If it looks at only layer 2 to layer 4 header, we call it layer 4 switching. So it will look at your Ethernet address, source address, destination address, generally not, IP source address, IP destination address, and the TCP port number, source port and destination port. All right, those are layer 2 to layer 4 headers, key header fields, and based upon those it could decide. It could be just one field, for example, the source IP address. That's it, done. But if you look at WASU has at the external end, maybe it has one connection. Somehow it goes, if it's a big organization and it has only one, actually WASU is not a good example. But let's take a company in some other country which has just one IP address and 2,000 people behind it, or maybe 20,000 people behind it. There are a lot of requests coming from that IP address. Right? So then you need more than IP address to balance the load. Layer 7 switching is then when you look at more fields, which means include layer 5 through 7. And really in TCP IP world, we know that there is no 5 and 6. So this is layer 7. And so if you look up that, then there is layer 7 switching. Okay, if you want to send the video to this side and to this server, and you want to send the accounting to this server, you have to look inside the application field and see what it is about. You cannot just look at the TCP port number. Maybe you can look it up if you have programmed it like that, but generally, they will be all connecting to the youtube.com and port number 80, and now you have to go to inside that port number to figure out whether it is a video request or a directory search. Right? So you look inside the layer 7 header or layer 7 event data, and that is layer 7 switching. And if you want to do layer 7 switching, the problem is you don't see layer 7 until the TCP connection has been accepted. So first somebody says, okay, I want to connect to this server, and now you don't know which server to send, because you don't know whether they are going to send video request or accounting request. So you just accept the connection. Who accepts the connection? The load balancer. The second time they say, okay, I want this video. Now you look at the video, you say, okay, it goes to server 1. Now we connect it to server 1. All right? Now even though it might be a connection from you to them, but at least you know that you have sent it to server 1. So when the next time they request something, or the second piece of the same video, or the second frame of the same video, you send it to server 1. Or if they send a stop request, you send it to server 1. Even though there might be two TCP connections, but they are really connected. All right? So the layer 7 switching requires delayed binding. Delayed binding means that we don't know the server until a application request comes in. Whereas in the previous case, L2 to L4 switching, you have immediate binding. Basically, you just pass the request and you're bound to that kind of server, right? Yeah.
Could the binding be changed when the TCP connection is on during one session? If there is one kind of traffic being exchanged, video to video server, could the binding be changed to another server in the same session?
Okay, if you need to do layer 7, it is better to just
terminate the session and
terminate the session and terminate the connection, which is segment, and then start a new segment. That way you can flip the other segment part as you want, as you need. Okay. By the way, this is the PhD topic of Subharti. So Subharti can tell more if there is a difference on this one. You agree with all this, right, so far? Yeah. So symmetric connection management. So now, traffic in both directions passes through the load balancer. That is one option. And second is asymmetric, in which only passes one side and doesn't pass the other side. All right? That creates lots of problems, and so generally not used. But in symmetric case, once you send it to the server, server sends it to you, and then you send it to the customer. All right, even if it is layer 4 switching. See, in the layer 4 switching, you have the option of giving it to the server, and the server can send it to whichever way they want. Right? But generally, even in that case, they send it to, and actually we have more slide on this one later on, just after this. So there are two ways of connection management, symmetric and asymmetric. In symmetric, both directions passes through the load balancer. In asymmetric, one direction passes, the other direction doesn't have to. So load balancing using DNS. What is DNS? Is the domain name system. So that is the first way people came up with the idea of doing the load balancing. So the way they did it was that when you go and ask for google.com, every time you went to the DNS, it will give you a different answer. Okay, so you will randomly go to some server, next time you go to some other server, next time you go to some other server. So that's the cheap and easiest way to do. You don't need any hard box or anything, just load name server. And so it gives you, but what it does is, what the DNS does is, and this is a standard DNS, is that every time it gives you a list, it rotates it. So that first time it will say the DNS address is 201.202.203. Second time you go, it rotates it by 1 and says the address is 202.203.201. So what happens is most people will just take the first address and start. Alright? Third time you go, it gives you a different one. So in fact, after I printed your handout, I did something called NS lookup on www.google.com, and this is the answer I got. Okay, you see the list here? For the Google from my computer and my office, these are the addresses possible. All of these are www.google.com. And if I did it again second time, the list will be rotated and given to me. You can just check it out on your computer. What is the Mac command for NS lookup? Anybody knows? Huh? I am sure. Huh? What is it? Okay, so I think NS lookup even might be a Unix command too, but this is on the Windows I did. NS is name server lookup. Okay? And you can put any name and it gives you the list. What? Date? DIG. Dig. Okay. Alright. You figure it out from Mac. I am a Windows guy, so just want to make sure. Alright. So rotating DNS is used for load balancing. The problem with this is that it doesn't know the geolocation of the servers. It doesn't know that this server, the second one, is in China. Right? Or that this one is in India, or that one is there, so it doesn't know the geolocation. It doesn't know whether the server is loaded. It doesn't know whether the server is up. You gave the address on January 1st, and then you are asking on December 31st again. Who knows what happened to those servers? Right? It doesn't know whether the server is up, and adding or removing a server is too slow, and DNS is too slow. What happens with DNS is, everybody on the way caches the names. So when you ask for the google.com, it is not coming from Google. It is coming from the DNS in your computer first. If your computer doesn't know, it asks, the network DNS. If that doesn't know, then it asks, the site DNS. If site doesn't know, then it asks, blah, blah, blah. It goes all the way to the root. So there is a whole hierarchy of people, and all of them remember the previous answer. So they will all tell the old answer. Alright, so if you do change, suppose Google does give up one address, it will take months before the address will get out of everybody's DNS. Okay, talking about the DNS, there is an interesting story I need to share with you. So basically, at one point, and this is old days, not now, one computer in Pakistan said, I am, and I think it was youtube.com. Okay, it resolved, if you ask for youtube.com, it gives its address. So all the youtube.com requests went to that computer in Pakistan. Alright, so there was and suddenly this is like youtube.com being attacked, which means they are not getting any requests. All requests are going into the drain. And so this was possible before. Now all the requests are authenticated, all the answers are authenticated, responses are authenticated. So you couldn't, you could fool up to a certain point, but if you go beyond that point, you will get an authenticated answer.
Pakistan thing was not the DNS, it was because of BGP.
BGP.
So,
Okay, BGP. Okay, all right. I got the answer. So it was because of BGP, because the BGP set the route to this address, which was youtube.com address. Which address was correct, but in the wrong place. Thank you. All right. So now people are selling what they call global server load balancing.
So we have a question.
Yeah.
Previous slides.
Yeah.
Is the resulting IP address is that address for the load balancer or the servers behind the load balancer?
Okay, that we don't know. But that is where you connect to. Now that could be, I would be really surprised if that is a real RP. This is not real IP. This is, actually next slide will make it clear. So let me just explain this one. So you might have your application in many different clouds, many different locations. Each location has many servers. Each location has many balancers. Each of them have what we call virtual IP. And these are the real IPs on this side. So then you put this box, which is actually a DNS modified. This is a smart DNS. So when somebody sends a DNS request, it knows which of these are up and just only gives that list. That's all it knows. Somebody is up or down. And the reason it knows up or down is because it keeps sending the pings. All right? And not only is it sending the pings, because this is designed by the company which is making all this, they could also put that this address is in China, this is in India, this is in USA. If the client is coming from USA, they will give this address. If the client is coming from China, they will give this address. So this is a smarter DNS. Okay? A specialized DNS server that keep track of the server location and states. So there are two things they know. However, nobody will come to this DNS because they have their own DNS, unless they came to the basically authentic answer. If you don't ask for authentic answer, anybody can give you the answer whatever they know from before, right? But if you have just one company, inside the company you have just one DNS server, then this is the server and this will get to the right place. Or if it is one data center and this is the server, it will get you to the right place. Right place means it will divide your load the way you want it. So this is, while it is sold and bought and everything else, this is an appliance that is sold by some company. This is generally good for intra-company use. Okay? I think this answers your question. Your question was whether it is real IP or VIP given. So you say the name server only gives you VIP. And if you want it to be real IP, that doesn't matter. Don't put a load balancer and then the server will get it. Okay, any other question? Yeah.
yeah, the last slide. So the IP address on the slide is the VIP or the real IP?
This one?
Yeah, this 74.
Yeah, these are all VIPs. I think that was the same question you asked. Yeah, these are all VIPs. This is where you connect to. Now, given most applications the way they are today, I would be surprised that if it is a very small application, then you might just give a real IP. Because you really want to have lots of servers there at that address.
Yeah. So we don't get to the real IP.
Generally, we don't get. Generally, let me just say, see, the thing is, every statement I make is only 90% true. Okay? Generally, we don't get. But, there are applications. I use VIP in my home. So I have a server. And I ran into this problem, the server became hard, so I put another computer, then that became hard, then I had to put another computer. So every day I have to change the server. Finally, it came to my mind that every time I change the computer, I should change its IP. So that I don't have to change everything else. And this basically that IP is used by security cameras. Security cameras use an FTP server to put all the pictures there, and you reprogram the computer and file servers and everything else. I mean, you have to reprogram everything for every time you change the server. So you give a VIP, and then whichever is the server that day uses that VIP. All right. So load balancing more. So now we know DNS part, but then we need to learn about something called NAT. NAT is network address translation, and there are three types of load balancing NATs: dual NAT, server NAT, transparent NAT. But before I describe those three, I really need to explain to you what NAT is. So I'm going to the next few slides are NAT, and then after we are done with the NATs, then we come back to these three. So network address translation, again this is 473, but since I need it here, I want to make sure that you know it very well, is that whenever you have private network, you have private addresses, those addresses cannot be used as the source address on the public internet. Alright, so what you do is you put a network address translator here, and whenever something goes, it always goes with that source address, which is a public address. Everybody knows what is a private address, right? And what is a public address. So this is a public address, and you have only one public address, and so you just use all the computers are private addresses, and then you use that address. So the private addresses cannot be used on public internets, so the NAT overrides the source address. When you send a packet, the source it looks at the IP address and changes it, and then it makes a note. It says, okay, well, I got a packet from 201, and it was going to that destination, and so when something comes from that, it sends it to 201. If it came from 202, it sends it back to 202. So, and there is a little bit more detail. Actually, it also changes the port number, because if there are two people going to the same destination address, and the response comes back, it has to know which one. So it looks at it changes the source IP and the source port number. Source port numbers are random. So the destination port numbers are standard. When you send an HTTP request, generally you have to send it to port 80. But you can put any number in the source port, and it doesn't matter. You might put 3043. Okay? It will change that number. The NAT will change it, and so in the table it has that, okay, this 3043 was from 201. When the response comes back, it has the same port number in the destination field, and it changes it back, the destination address to 201, and the source port number back to your 3043, whatever you had put. That's how the NAT works. The only problem with NAT is that only allows outgoing connections. It doesn't allow incoming connections. So for example, if you're running a web server here using port 80, if somebody wants to come to you, this box will not know where to send port 80 to unless you program it exactly. That's what you do on a router, home router. You have to program that which computer out of your 10 computers gets port 80. No other computer can get that port. So you can do port mapping. But if you don't do port mapping, then the incoming things cannot possible. Only thing, when you send out something, you get the answer back. Send out something, get the answer back. So here's an example. There are two computers, one IP address, and so 201 using source port 8001 sends something. Doesn't matter where it sends to. So let's say here is the detail. 201 sends to 210, to this IP address, with the source port of 8001, the destination port of 80, so which is a web server. To this web server sends a request. The NAT changes the source address to the public address and changes the source port to a random number 3001 and makes a note. Actually, it's not a random number. It is smartly puts in by the row number. So it says, okay, in row number 3001, I have remembered this entry, so it will put that number here. And then the packet goes to the destination. The destination basically reverses these. So the source becomes destination, destination becomes source on both IP and TCP. So the destination is 216, which is the public IP address. The source is this thing, which is okay, and the destination port is 3001. Okay, and that is the key. So now when the NAT gets this packet, it looks at 3001 and looks at that entry and it says, oh, this actually came from 201 with the port of 8001. It changes those two fields, puts the destination of 201 and the port of 8001. Okay, so now you see this source does not know that it really went through NAT, because it sent to whatever source and destination, it got the same thing back, similar thing back. You see? So the NAT is hidden totally, is actually in that sense, if you want to call it in a ADC, because it is a service that it is giving, and that service is to use a single IP address. But so basically, this is how the NAT works. Now this is called I'm missing something here. Let's see. Okay. Anyway, this is called NAT 44. This is called NAT 44 because your internal private network is IP4 and the public network is IPv4. Alright, but it doesn't have to be. You could have an internal private address of IPv6. The public network could be IPv4, and the NAT will do the same thing. Yeah.
The NAT 64, is that a IP4 tunneling? You put the IPv6 packet?
It will use tunneling, yes. Good point. Is that you cannot just change the address and send the packet, because IPv4 routers will not understand the rest of the packet. So IP NAT 64 will not only change the addresses, but it will also encapsulate the packet so that everybody on the way will understand. Only the destination at the end will de-encapsulate it and then figure out what to do with this packet. But you can go through the public internet, IPv4 internet. Similarly, there is a NAT 46 which does just the opposite. Okay, everybody understand NAT 64, 46, and 44? All right.
What is the dual state server queue?
Huh?
What does the dual state server queue mean? What's the dual state server?
Dual stack.
Dual stack. Yeah, okay. So the technology, basically, when it was designed by a graduate student at Stanford, IPv6, they asked him as to how you are going to support both B4 and B6. He says, I will put both these stacks in a single router. Okay, so the router gets it and it says B4 or B6, and that is what. Okay, well, that was really not very smart, because nobody is going to buy two routers for the price, are going to pay the price for two when one will do. So that's why the V6 is having difficulty coming in, is because there is not good transition strategy. So anyway, the dual stack means that you implement both. So that is one alternative, is that you implement both in the router system. So right now, this is the situation in the world. Every host implements both. Microsoft Windows implements IPv6 and v4. I have this laptop in front of you. It has both IPv6 and v4. Alright? But none of the routers do. When you buy a router, it either is IPv4 or it is IPv6.
Why you can't?
Because it's twice the cost. Well, it's not really twice the cost, but it's extra cost for nothing. So the idea is, the idea is that also there are lots of already routers in the world which are IPv4. They're not going to change them to make IPv6, because the fields are different lengths and everything else is different. It's not just firmware upgrade, it's a hardware upgrade. And why break something when it is working? Alright? So these NAT kind of things will help, because then you are just encapsulating and doing that, right? So this allows organizational carriers to transition. So now the carriers, particularly in the other countries where the IPv4 addresses are in short supply, are thinking what to do. So they have come up with carrier grade NAT. Carrier grade NAT means that they are going to use a NAT themselves. So they will have one IP address and they will give out their private address to everybody, not public address. Right now in the United States, when you go to AT&T or Cox or anybody, you get a public address generally. They don't make a bunch fuss about it. But if you go to some other countries, there they don't have that many private addresses that they can give to whole city. So they have to give out private addresses. All right? And then that address actually, it turns out if they start giving 192, there will be a lot of confusion because everybody has 192. So they cannot use 192. So they went to IETF and said, please give us something which other people cannot use. So they have a carrier special private address, which is called shared address range. And that starts with 100. Okay? 100.64.0.0/10. Everybody understands how to read this /10? How? How long is the prefix? 10 bit is the prefix. So you just write this out and first take the first 10 bits. So first 8 bit is 100, and out of 64 you will get 01 because 8 bits is 127 and onward, right? So you get 01. So that's all there is a prefix. That prefix. So they can give out this number. So they can give out 1064.1.2 to this customer and 1.3 to this customer. Now this is, for all practical purposes, is a public address for this subscriber. It will have a NAT to switch to that, and then the carrier will have a NAT to switch to the real world.
There's any delay.
Huh?
There is
a delay. Everything requires time, right? But better than having no connection. So, several concepts here. First concept is here you heard about shared address range. This is new stuff. Shared address range is 100.64/10. Second thing you heard is the carrier grade NAT. Third thing is NAT for 4.4. So there are 3 4s here. 4, 4, 4. Now you could have other combinations. Can you think of other combinations? something like that, right? Here could be 6, here could be 6. Here it has to be 4 right now, in the middle. Because shared address range is only for the 4. Here's the reason why you don't need the 6 there. Because if you had a 6, there's no shortage of addresses. We could give it out to everybody. Right? We need these private addresses and we need these shared addresses only for B4. Yeah.
So can the shared address be used by any institution other than carriers?
No, actually, so here's the thing. Anybody can fool anybody. So this is designed for the carriers, but there's no police on the internet. So you can use it, Vashu can use it, and police will not come, except if suppose AT&T starts using it and Vashu uses it. It will have to be very careful that there is no confusion here. If AT&T is providing the service, here's the thing. Suppose this guy starts using carrier grade addresses inside here, there will be a lot of confusion because your neighbor has that address and you are sending out the packets. So yes, the carrier might police it. Carrier might throw away. Basically what this router will do is it will look, oh, is the address 1.3, it is coming from here, throw it away. Right? So of course the confusion will be there and the carriers can police it, but the internet doesn't have a police. Okay? All right. Now, a good thing is that every carrier can use this 100. So basically, Cox can use it, AT&T can use it, and every carrier. So everybody doesn't need a private, doesn't need a location. They don't have to go to IANA to get, okay, what is the address you can use. Right now, they go to IANA to get IPv4 addresses, public addresses.
So, but I think there is some limitation because port is limited. So
Port is limited.
Yeah, I mean, support is limited.
Support is limited.
No, I mean the port is, from 0 to the 5,000.
16 bits, yeah.
Yeah, I mean, so the port is limited, so it doesn't support everybody. And
Okay, so his point is, okay, let me explain what the point is. The point actually applies to all nets, and let me go back to this. See, the thing is, this port number that this net used is 16-bit, and many of these numbers actually are standard. So, for example, up to 1024, they are standard port numbers. You cannot just arbitrarily use them. If you use port 80 for something, there will be a lot of confusion when the response is coming back, because a lot of people will think that 80 is a web page. So you don't use that. You can use it. There's no reason that you cannot use port 80 as a source port, by the way. You can use any number you want. But just to avoid the confusion, because firewalls look at port numbers. Alright, your firewall might be confused if you use the wrong port number. So generally you use only from 1024 up to 2 raised to 16. Alright, so his point is that you have approximately 2 raised to 16 port numbers, and therefore your NAT is limited to 2 raised to 16 computers. Alright, yes, that is true, but 2 raised to 16 is good enough. Alright, so here is the thing. In this carrier grade thing, we are almost reaching the limit, because this NAT has 2 raised to 16 subscribers it can have.
you mean 2 to 16, right?
Yeah. Alright, 2 raised to 10 is 1,000, 2 raised to 64,000 customers it can have.
So it doesn't support the city, right?
Hmm?
It doesn't support the city. I mean, the small villages support the
64,000 is not supported in all city. Oh, you can do easy. I mean, all you have to do is just create another carrier. I mean, you could have AT&T 1 and AT&T 2.
Oh, okay.
I mean, only one public address here, right? I mean, you don't want to put 16,000 people on one address.
I see.
All right, what you do is you put them on, totally slightly different box.
Yeah, right.
Okay? All right, now we are back to our previous slide. Now that you understand NAT, we can talk about how you put load balancer. So the load balancer can just do dual NAT, which means that it does both sides. Now this name one arm mode, actually I saw some of the vendors, actually I should say, like, there are many vendors, Cisco, F5, many people who make these load balancers. They all use different names because these are not standard names. Okay, so dual NAT is Cisco name, one arm mode I forgot whose name it is, but there are other companies use other names. So there are two names. So it changes both the source and the destination addresses and the destination port numbers on the client request, like a regular NAT. So this is like a regular NAT, right? So what happens is when the request goes, the source address is different now. You see here, the load balancer says that the source is 168.0.1, which is me, right? And the port number is 3001. So when the server responds, it sends it to the load balancer. Load balancer looks up its NAT table and says, oh, it came from that host client and his port number was this and this. So it just does just like a regular NAT. That is called a dual NAT. Okay. Now the server sends a response to the load balancer, and the client and server can be on the same subnet. All the story I made. Okay, so that is the positive part. The negative part is the second line. So positive and negative. Positive is the client and server can be on the same subnet, but the negative part is that the servers do not see the real client address. So when this server gets this packet, it thinks that the 01 sent it, which is why the servers want to know who sent it? Is there a reason they would want to know who sent it actually? Huh? Firewall and security and other reasons. Somebody is not supposed to write on this thing, right? So they really don't like that they don't know who sent it. That's the negative. this is actually okay here. So client and servers can be on the same subnet, because here the thing, basically this will send it to this VIP, and all the VIPs could be 192 here. Okay, it will get there, and it is going to change both the addresses, and both the addresses will come back here, and they will go back to the place. So there is no problem here. There is no bug, there is no mistake in this slide. You understand, the positive is that they can be on the same subnet, but the negative is that the servers don't see the real address which they want to see.
So you mean the client and load balancer in the same subnet?
They can be on the same subnet. Everything, this whole thing could be one subnet.
The servers have the private IP address, is not the.
Yeah, so I'm saying, suppose this whole thing is inside a data center, single data center. They could be on the same subnet. They could have same private address range.
Then of course NAT would not be.
No, hold on. No, NAT here is a load balancer.
Yeah, but
See, this is the thing. All I'm trying to tell is the one way to load balance is by NAT, using a dual NAT. You don't need NAT for address translation. You are using the NAT technique for load balancing.
To be the same subnet, the client will also have to have address of 192 to 168 in that range, right, as a server's have.
Yeah.
Which in this case is not possible.
In this case is why?
Right now, your client has 128 or 252, right?
No. Here's the thing. Let's say everything is 192, but when we are declaring the address of this server, we are not publishing these addresses.
Just put 0.1.
We are putting 0.1. That is the VIP, virtual IP. So all the clients will come here. From here they will go to different servers, and then they will come back here and then go back to all the clients. So this works inside a single subnet. As you see the different techniques, they have this positive and negative. So the second one, which is called server NAT and called routed mode, in this one it changes the IP address only but does not change the port number. Okay? So now what happens is server sends the response directly to the client. No change to the port number. Actually, no change to the source IP address either. You see? So the request is coming from this source IP and this source port. It is sent with the same source IP and the same source port, except the destination address has been changed to real IP. Alright, now the server can send a response. It will just flip these two destinations and source and send it, and so let's see, 216 is outside, the port number is 8001. Load balancer is made the default gateway. So the only way, okay, so the problem here is this packet actually has to go through the load balancer, and the way it will go through load balancer not by the address, but because it is the default gateway. You know what is the default gateway? All the packets go through the default gateway. So now, if you make this a default gateway, so this packet will go there, the load balancer will look it up and say, oh, okay, this request had come from, so it will change the source address here, 210 to virtual IP. So basically, this source address 02, real IP, will be changed to virtual address 210. That's all it is doing. It's changing the changing the destination here to private, and here changing private to the public. Public to private, private to public. That's all it is changing. No change to the port numbers. It's not even looking as to where it came from. It doesn't really need to know anything. All it needs to know is that it came from a public address, and I'm sending it to private address, and then whenever it comes back, it changes private to public. Yeah.
So servers, how the CAN servers can see the near client address?
Yeah, in this case, so now let's see. So we are up to here right now. Load balancer is made the default gateway. All the requests go through the load balancer because of that reason, and the load balancer changes the source IP addresses on the responses as well. So this works only if the client and the servers are on the different subnet. So this will not work on the same subnet, because on the same subnet you do not go through what? You don't go through what? Gateway. If you are on the same subnet, you can talk directly. You don't need to go through the gateway. So this one requires that this be made a default gateway, and then only it will go through that one. But the advantage is the server can see the real addresses. So we flipped the advantage and disadvantages from the previous one. That answers your question?
Look, I mean, servers only see this destination's IP address, the low.
It says the correct source address.
I see.
Source address 216.
I see. Yeah.
Alright, the last one and the last slide for the day is transparent mode, direct routing mode. All servers are programmed to respond to the same VIP. So now here we are manipulating the servers. And servers have two addresses, a VIP address and an RIP address. VIP address is 210 for all of them. Alright, now multiple people having the same address could be very confusing. So what they do is, they tell the servers, please don't respond to ARPs. If somebody asks you, what is your MAC address, don't even tell them. Because otherwise they will get 3 responses and they will be very confused. Right? So the servers have 3 VIPs. They have some real IPs too. That is what they really, if you want to manage them, if you want to change something, you want to tell something, then you use the real IP. So they have 2 IP addresses on the same port, 2 IP addresses. One VIP, one RIP. VIP is used for the service and RIP is used for management. So when somebody sends, they send it to VIP, and the load balancer basically all it has to do is flip. Send it to 1, 2, 3, 4, 5, 3, 1, 4, 5, whichever, doesn't matter. So everybody has that same address, the answer goes back. Okay? And load balancer has to be something in common, because the thing is otherwise it will not know who to flip where, because it has to flip it back and remove the connections list and all that, right? So basically sole layer 2 switch to the server net, it does not change anything. It does not change the IP address, port numbers, nothing. That's why it is transparent. Okay? Alright, I'm going to stop right here. The whole thing in this lecture today came from one book. And the book is referred at the end, reading list. I would recommend that you read that. Okay? And there will be a quiz at the beginning of the next class. Alright? So, please read. Any question? There is no homework other than the project homework too.